That's going to go into our mind map, and it's a screencast covering the concept I talked to you about in lecture 2, which is the periodic table, and we're starting to consider atoms as nature's building blocks. So if you remember in lecture 2 I talked very briefly about the generic structure of an atom, in that you have a nucleus that contains protons, which are positively charged, and neutrons, which are electrically neutral. It's these two that give the atom its mass. And then in the volume around the nucleus you have orbiting electrons, which have negligible mass, but they're negatively charged, so they counteract the charge of the protons. And for an atom to be neutral there must be as many protons as there are electrons. So you can work out the number of electrons an atom will have by knowing the number of protons in its nucleus, because it would be exactly the same. So that was as much as I could say about the generic structure of an atom. Well, they then went on to look at the periodic table, and I showed you what the periods are and what the groups are, and we looked at the key groups for us, and we highlighted that region where all of the elements that are found in organic molecules exist, which is only a small part of the periodic table. And I posed the questions, why do we need to know the positions of elements within the periodic table? And I do say to you that you need to be very familiar with the positions and the properties of the most important elements in the periodic table. And the reason for this is that knowing where an element is placed in the periodic table allows you to work out its important characteristics, so things like the atom size or the electronegativity. And this is important because it's the atoms that make the molecules. They're the building blocks that make the molecules. So the nature of the atoms obviously then gives the nature of the molecule as a whole. So we need to understand the constituent parts to fully understand the nature of a molecule. So then I put the periodic table up again and talks a little bit about the periodicity, the patterns that we should be familiar with for this life sciences chemistry course. And the ones that I wanted the students, or I want you to be aware of, is that as you go down a group, you increase the number of protons and electrons that are present, and you increase the atom size, and you decrease the electronegativity of that atom. Whereas if you go from left to right across a period, you actually, even though you're actually adding more protons and electrons again, you actually decrease the atom size here, and you increase electronegativity. So these two are opposing, and these two patterns are opposing, and on face value this seems a bit confusing, and we then went on to explain this in the lecture. So as you go down a group, you're adding electron density, but what you're also adding is you're adding shells. So these extra electrons are being subsequently added to valence shells that are further away from the nucleus, and have, as you go down the group, more and more shells between the nucleus and the outer shell electrons. And it's these electrons in the shells in between the outer shell and the nucleus that shield the electrons in the outer shell from the pull of the nucleus. And that's why as you increase the number of shells between the electrons in the outer shell and the nucleus, you increase the atom size, because the electrons in the outer shell are being held less tightly, relatively speaking, by the nucleus, and therefore they're existing further away from the nucleus. And you're decreasing the electronegativity as you go down the group, because again you've got this extra shielding effect from the electrons in the shells between the outer shell electrons and the nucleus, so the pull of the nucleus is being felt less. Conversely, when you go from left to right across the period, you're adding extra electrons, but you're adding those electrons to the same shell. You're just filling up the outer shell as you go from left to right. So you're not significantly increasing the amount of electron density between the nucleus and any of the electrons in the outer shell. But what you are doing is you're increasing the size of the nucleus as you go from left to right. So you're increasing the size of the nucleus, and you're not increasing the amount of shielding between the nucleus and the electrons in the outer shell. So consequently, as you go from left to right, the electrons are being held more tightly by the nucleus, therefore we see a decreasing atom size. And because you have these larger nucleuses on the right here, these have got a greater pull of the electrons, and because there's not significant shielding, then therefore each of these elements here are going to be very electronegative, i.e. they're going to pull very hard at electron density, because you've got, relatively speaking, a large nucleus and not much electron density to shield any other electrons from that nucleus. Okay, so these are the key points, the key patterns we should understand in the periodic table for this course. So we put that in the context of considering atom size. Yeah, and what we said was that the size of an atom is basically depicted by the size or the size of the orbitals in the outer shell. Yeah? It's the electrons and how far away they are from the nucleus that is the recorded sort of atom diameter or atomic radius, which is the more common way of thinking it. So the further away an electron is from the nucleus of an atom, the larger that atom is. And that's what we need to bear in mind. That's what we're talking about when we talk about sort of the size of an atom. So this led us on, so talking about atom size, then led us on to thinking about orbitals. And what we said is that an orbital is a region of space where the probability of finding an electron is large. So what we're saying is every electron that is orbiting the nucleus of an atom is put into an orbital. And all that orbital is an area around the nucleus where it's been found that the electron will exist 90 to 95% of the time. Yeah, so it's a lot of quantum mechanics that have developed an explanation or a prediction of where an electron will be around a nucleus at any time. Yeah, and the 3D shape of a molecule is determined by the nature and shape of these orbitals that the electrons are in. And then we flashed up our first electron configuration diagram, and we went on to say that each of these lines in an electron configuration diagram represents an orbital. And then the rest of the lecture was talking about what 1s and 2s and 2p means. So I said that the two important types of orbital for this course are the spherical orbitals, which are s orbitals. Okay, they're always spherical. So what we're saying is that this black dot in the middle is the nucleus, and if there's an electron in this s orbital, then 90 to 95% of the time you will find the electron in this spherical area around the nucleus. It'll exist in this space around the nucleus, and this is said to be that electron's orbital, where it's most likely to be at any one time. And then the other type of orbital was this p orbital, which is dumbbell shaped, and we say that this p orbital has two lobes, where the area depicted in the blue colour is a lobe, and then this dot in the middle is said to be a node. So the lobe, very much like this red area in the s orbital, this lobe is a region in which you're likely to find the electron in 90 to 95% of the time, and the electron is just as likely to exist in either of these lobes. And a node is just an area where it's been found that there will be zero electron density. So the electron will not exist in this area if it's in a p orbital. So this shape, this dumbbell shape, is just describing where the electron is likely to be found if it's in this p orbital. Okay, and then we went on to say that the greater the number of nodes, so this is a node as described here, the greater the number of nodes, the higher the energy of the orbital. And we also said earlier in the lecture that the further away from the nucleus that the orbital or the electron is, the higher energy that electron will be. And then the final key point, we said that each orbital can hold 2 electrons. So each of these orbitals can accommodate 2 electrons. And then the final sort of description of p orbitals that I gave was that in any one shell there won't just be one p orbital, there will always be 3 p orbitals. There'll be one and they're all mutually perpendicular, so they're all at right angles to each other. One will lie in this z-axis, if you will, one will lie in the x-axis, and one will lie in the y-axis. So these are the 3 p orbitals together. So you can see this is your dumbbell shape here and here, and this is your dumbbell shape here and here. Okay, and then there's your third p orbital there. And because these are all the same shape, they have the same number of nodes, these p orbitals, they each have one node, and because of the same size, they're all at the same energy level, and orbitals that are of the same energy level are said to be degenerate. So every shell from the second shell onwards will have 3 p orbitals in it, and each of those p orbitals will look like this. They'll each have a node where there's no electron density, and they'll each be the same size, and they'll be the same energy level as each other, so there'll be 3 degenerate orbitals. Atoms can also contain d and f orbitals, but we're not going to concern ourselves with them in this course. We only need to know about the s and the p orbitals. And then we just quickly at the end looked at now what we understand about this electron configuration diagram for a carbon atom. So what this sort of diagram is saying now is that here we have the first shell. So we can put this line in to say that this 1s orbital is the first shell of that atom. There's just an s orbital in that shell. That orbital will obviously be spherical, yeah, and it will contain 2 electrons. And these 2 arrows here stand for 1 electron each. So this is 1 electron, and this is the other. Okay, so there's the first shell of this carbon atom, an s orbital containing 2 electrons. Then when you go up to another shell, you add another set of orbitals. So we're adding the 3 p orbitals at this stage. So the second shell now contains s orbital, again containing 2 electrons. And then you've got these 3 dumbbell-shaped p orbitals that are all at the same energy level. So we can put our energy in here on this axis, and we can see that the 2 p orbitals, these 3 orbitals here, are all the same energy level, but they're higher energy than the s orbital. And the reason for that is that the orbitals in the second shell are further away from the nucleus than the ones in the s orbital, so therefore all of these are higher energy than this one. And then you can then say that the p orbitals in the second shell are higher energy than the s orbital because each of these p orbitals has a node. And that's as much as we've gone into electron configuration diagrams, but we're going to explore that a lot more in the next lecture.